Welcome to Hochschule Karlsruhe. Welcome.
The EU4M program, supported by the Erasmus Plus program of the European Union.
Yes, and also to the EU4M program, it's an Erasmus Mundus program, and we have seen in the last years that our students are doing great work, and we wanted to give you, the interested public, parents, friends, partners from other universities, the opportunity to see what great work our students are doing, and this is why we are here tonight. We're giving short introduction to their work because we want to give you a broad range of projects that we wanted to present in a short amount of time, and that's why each of them will speak about 2.5 minutes, and after these 2.5 minutes are gone, the next one is coming, and right at the end there will only be the Q&A session where you can ask questions here if you're present in the room, or you can also ask online by putting your questions into the YouTube chat. You have to link it also to the project so we know whom to ask about your questions if we are not seeing it at the right first moment. So I'm really glad now to hand over to the first talk.
Hello everyone, my name is Maria Martinez, and today I will be presenting to you the project I laid last semester as my project Arbeit. This app is called Visual Flow XR. It is an app that I made with some bachelor students of engineering and architecture here at the HKA. First of all, we began wondering this problem. How could we make an app that would help architects and interior designers across the globe in their early stages design, focusing specifically on these two things. One would be the floor and tube planning, but also providing a cost tracking system for them to keep a track of their expenses. For this, we made use of the Unity software in which we developed various assets and also adapted some that were already existing into our needs. For this, we made use of some things like menus that would be as the settings, but also radial menus to be used within these controls and the VR headset. We also used some props of a garage, and the most important thing was the pipe builder. This is an asset in which you can construct different pipes and join them together. Another crucial aspect in this project was the real materials, which meant that we wanted to provide the audience a real impression on how their tubes would look like later on. These are some of the functions that we implemented. One of them was the room scan. When you first get into the room, you make sure to input that information into the app to later work on with your assets. This mesh allows the user to have control of the room, and from there on, you will have different menus that will help you develop these pipes. For example, in here you can see how the new pipe menu looks like, and also how the first stages of placing the pipe look. Some of the adjustments you can make are related to the diameter, the length, but also the material. In here you can see how one can edit the pipes throughout the room and also changing the connection and the nodes. We have a pipe manager that simplifies all this process. As I mentioned, one of the most important aspects of this project was the cost tracker. This is a counter that is integrated as a function in which we see the budget being modified depending on the length of the pipe, but also on the diameter placed and the material that it's going on. This value can be changed throughout the whole time, and the designer can adjust it so they don't overexpend. Thank you very much for your attention.
Good evening to you all. I would like to give you a quick overview of a project I worked on last semester. It's about the calibration of an automotive R&D instrument, and I worked on it in collaboration with a local company. The goal of the project was to build a field calibration system for the devices you can see here on the slide. They are automotive data loggers who usually be installed inside of developmental cars. These data loggers can do a great many things, but relevant for this project was the fact that they can also measure voltages on 6 channels. A quick overview of the electrical system of the project, starting with a precision calibration source, voltage source, which then gets switched on a multiplexer circuit board to switch the precision voltage to each of these 6 individual measurement channels. During the course of my project, I mostly worked on the software components of the device, which meant writing interface components for all the different devices necessary, and also to use the calibration procedure, which I will get to in the next slide, inside of the software. Also a component to build PDF protocols. To the actual calibration procedure, I derived the procedure from the German national standard, the VDE, to calibrate electrical measurement instruments, and I specialized the general procedure for my purposes. Starting with a quick check of the prerequisites, things like ambient temperature, if all the necessary hardware components are reachable via software. The next step there are the measurement points taken. There's a total of 15 measurements to be taken for each channel, so a total of 90 measurements. Then there's an option to write the adjustment values of the calibration back to the EEPROM of the data logger. That's optional. If that's done, in any case, the results of the calibration get logged inside a PDF protocol, which is dynamically generated at the end of the procedure, along with any errors that might have occurred, so you can debug them later. Thank you very much for your attention. I'll give over to the next presenter.
Testing. Hello. Good evening, everyone. My name is Yong Ching, and today I would like to present one of my favorite projects in the last semester, which is OptiSkate. So it has the meaning of optimization of inline skate. As we know, inline skate learning is a difficult learning path, which requires us, especially for the beginner, to learn by trials and error. Maybe they fall down and stand up, have to do it more times. So in this project, we are aiming to introduce our mechatronic system in the inline skate to provide a more scientific and effective way for them to learn without professional guidance. So during the development, we have the hardware part of 3D printing case with the upper and lower part to clamp our force sensor and integrate it into our inline skate system by computing with the microprocessor ESP32, and we analyze and compute the data into the graphical way, which we can see in the next slide. And the electronic part, of course, is connected and work together with the Arduino. And this is what we did in the simulation part. Of course, we faced some problem during the development and also simulation, which is we have to determine which orientation of the sensors are the best for the user and also for the real-time data acquisition. Also, we solved the problem step by step, and we come out with the happy result with different techniques, for example, turning, P-stop, and also sliding. So with these results, we are hoping in the future project or development, we can integrate into, for example, a mobile phone or a simple app that the user can be used as a guidance during their learning process in the inline skate. Thank you for your attention.
No? Good evening, everyone. My name is Nebojšević, and I'm a student of mechatronics master's degree here at Hochschule Karlsruhe as a part of EU4M program. Today I would like to present you the project Arbeit that I did over the past semester under the supervision of my professor, Professor Fahmi Belaluna. So the goal of the project was to experiment with the depth camera, Intel RealSense D455, in order to see what the features it has and the possibilities and real-world applications. So the camera itself consists of a left and right imager, infrared projector, and RGB sensor, yes. So in order to interface with the camera, we need a software development kit, which in this case is NUI-Track. So NUI-Track is a SDK which allows users to see the full body skeletal tracking, to make user masks, to obtain a 3-point cloud, gesture recognition, and face tracking. To finish this project, we had to use some other software, which in this case is Unity 3D. And you can see the results on the video. I will speed it up a bit because the video itself is almost 2 minutes long. So this is my colleague Giovanna, and our idea was to make some kind of a virtual changing room. The idea was to implement the models from Unity Asset Store, as well as some gesture recognition and precise movements. But due to the scope of the project, we just didn't have time to do everything. So these are just some of the models, and that's it. Thank you for the attention.
Hi, my name is Ignacio, and today I'm going to present you my semester project, which is called Drivetrain System for a High Energy Efficient Vehicle, which is part of the Shell Eco Marathon competition here in Europe. So the task was first to build a complete new drive system for the current car. The first step was to design an updated chassis, because the one that we have available was missing important features such as mounting points, wall thicknesses, and etc. And after that, we could start to model the drive itself. So the main features of this design was to make all the designs of the sub-components, the parts, the sub-assemblies, like the wheel assembly, the frame, the drive mechanism itself. And the most important point was to keep it very light, because it has to be very efficient, but it also has to be very easy to manufacture, because students will be working on this car. So it has to be easy to manufacture and assemble. The results that we got with this project were from one side, all the calculations, like the calculations of efficiency of the motor, efficiency of the drivetrain, and for another side, we got all the manufacturing drawings of the parts and the assembly drawings, So we got all the documentation that's necessary for us to give to the next group that's going to carry on of this project, so they can build this design and they can implement it correctly on the current car. Thank you very much for your attention.
Do you hear me? Yep. Okay, so I'm gonna do like the continuation of the project I did with my previous colleague Ignacio. It's a 3D model of the drivetrain system for a high energy efficiency vehicle. I'm gonna talk a little bit more about the competition itself. Yeah, I think this is a really known brand. It's Shell. It's a British company that produces hydrocarbons. And they decided to create this competition to test the students from different universities to develop the most efficient car possible. The goal itself is to produce a vehicle that has to accomplish certain guidelines, mainly safety guidelines, and it has to travel the most distance possible with just 1 liter of gasoline. Here in the Hochschule Karlsruhe, we have one team that has been competing since 2011. And in 2018, they got their highest record with 1 liter of gasoline. They traveled 578 kilometers. Ooh. One of my main tasks here in the project was the developing of the tensioning mechanism. We decided to use a drive belt system. So it's important to have the exact tensioning for it, because if you tense it too much, if you tense it too less, it's not going to work efficiently. And also you need to have a special tension so it centers exactly in the pulley. Here, for example, how it works is we have this L-shaped metal sheet. Here on the top, we have the small pulley, we call it like that. That's where the belt goes on. And pretty much we use a turnbuckle, which is this component right here. You turn it, and it's fixed in one point, and in the other one, you regulate this movement, this linear displacement, which is also held by this hook right here. And yeah, pretty much pulls it downwards, so it tensions the mechanism. Also, we did finite element analysis. For the ones not familiar with it, finite element analysis is a computer analysis that you do in order to prove if the structure will hold, will bear the stresses that you put into it. Like, for example, here we're testing the braking force, which is the highest force that the vehicle will bear. And we can see here more or less with this video the representation of how it should behave. And in the next slide, we have more details about the numbers. So the maximum stress was around 75 megapascals. And the plastic deformation of steel starts at 210. So that gives us a minimum safety factor of 2.77, which is acceptable in this case. And we can therefore prove that the structure of the frame will bear the stresses. And that's pretty much it. Thank you for your attention.
Hello. Welcome to my presentation about my project, about this supply of a wind monitoring system by self-sufficing energy generator. I did my project with a company called Vika Mobile Control, and the company has safety systems for cranes. And one sensor is the wind speed sensor you can see right there. And the wind speed sensor is right now battery powered. And my task was to design an energy harvesting system with multiple sources that this sensor is not battery powered. The first part of my project was the design of the electronics. I needed to manage two energy sources. One is the wind speed, and the second is solar energy. That's why I designed an electronic circuit. With here you can see the simulation on the left upper side of the electronic circuit. Then I did a PCB design of the circuit, and then I assembled it. The mechanical part was to design an adaptive first prototype for the energy harvesting system for the wind speed sensor. And on the upper left side, you can see the construction of the prototype. And on the below there, you can see a part of my project I also had to do is a simulation test stand for the generator to simulate wind speed, to see how much energy someone can earn with it. And on the right side, you can see a picture of the test stand 3D printed. The main part of my project was the theoretical part. I needed to analyze how much energy I can win from the wind speed and from the solar cell from the iteration. And for the wind speed, I needed to analyze wind data in the location Karlsruhe. I used data from 2019. And then I analyzed the characteristics of the geometry of the wind speed sensor and combined this information to answer the question how much energy I can win with it. And the second part was to answer the question how much energy I can win with the solar energy. And I use iteration data from Karlsruhe also and analyze the characteristic of the solar cell I chose for my project, and then could calculate how much energy I would win with the solar cells. And then I tested my prototype, how efficient it is, and then the result, combining the information of the efficiency of the prototype and then the theoretical information I had, I could say I could reduce the battery capacity by 50%, and that's that's a good result for the first prototype. Yes, thank you for listening for my presentation. That's it.
Hello everyone. My name is Luis Sanchez. I made the project of a 3D object detection for autonomous driving with my mates Lucia and Vivek, which we'll present online. The first part will be Lucia, the one who is presenting. So I gave her the word. So Lucia, whenever you want.
It seems like we have a technical problem. Can you go on with the presentation?
Okay, I mean, I can do my part.
Yeah, do your part.
Okay, so, despite we weren't able to do the presentation, with the introduction, I do with my part. My part is about the implementation with some input data. In this case, I'm sorry that we couldn't explain to you how does it work, but I don't have time enough to do it. But But the main object is to detect for autonomous driving any kind of object. And to run our algorithm, what we did is train with two different kinds of input data set. We use for one side the NGSINs, which will be the one I will present, and for the other side, the Kitty model. So let's talk about the NGSINs. No, this. Well, the NGSINs consist of a total set of about 1,000 input sequences and scenes, which makes much more images. Well, as you can see on the screen, according to this input image, the output should give something like that, like all the cars detected, also some pedestrians, bike. Let's talk about the results we got. But first of all, the NGSINs, as it is a set of 1,000 sequences of images, is too heavy. I mean, a current laptop or PC cannot run that because it's, as I said, it's too heavy. So for such case, there is a mini version, which is the one we used, and that consists of just 10 scenes. And 7 scenes are used for like the training the model, and the other 3 for validation and testing. As you can see here in the table are the main parameters set for the NGSINs. I mean, explaining all of them will be to enter too much in deep, and there is no time enough. Also, there are some math parameters. I would put a point of the number of epochs, which is like a bit of explanation of this is like the number of iterations we did for getting the result. In this case, we did 20, and with these results, we thought it was enough to like refuse this project. I will explain right now why. Well. But first, let's explain the evaluation metrics. For the evaluation metrics, the main parameters are the mean average precision and the NGSINs detection score. The mean average precision, what makes is the evaluation of the detection algorithm's accuracy by computing the average precision of every class of object. And then the detection score evaluates the detection algorithms considering the localization and the orientation accuracy. For both of them, the higher the values indicates the better the algorithm runs. Here in this table, we can see like the general values for every sequence trained. First, we did with 10 classes of objects. And then we reduced up to the 3 main classes of objects, which were car, pedestrian, and bike, which were the ones like better detected and most probably to be found. And we got these results that compared with the voxelness reference value is way not too much. And also here is like the other table with all the results for every class of object we did, also for 20 epochs. And as you can see, it's not so high enough as the reference value. So with all those reasons, and also taking into account that this can only be done with a training version, we refuse to continue with the NGSINs, and we went on with the Kitty model. And from my part, that would be all. Yeah.
So right now we go on with Teams, and we will present online. We can't hear you yet, but you also.
Whatever.
We hear you.
Okay, perfect. So, good afternoon again. Sorry for the problems. Our primary goal was to adapt the voxelness architecture from GitHub for our 3D object detection task. We aim for a comprehensive examination of the voxelness architecture
so to
by
interrupt
testing
you, but
its
you haven't
performance
shared
in
your screen.
2 different datasets, Kitty and NGSINs. Luis already talked about one. And lastly, we'll dive into the performance of our model.
Running it, Salah, of course, is very quick, and he's not shy
autonomous driving
doing the defending when he
systems
has
are
to.
composed of several
He'd rather
functional
not.
modules, each playing a crucial
Gave
role
him the
in
respect there,
enabling
thinking, well, I
safe
can't run
and efficient
away from here.
navigation. Today we'll focus
When I was
only
talking about
on
him
2 key
not doing the
modules.
defensive side of the game, not because
First one,
he can't do it,
sensing.
he doesn't want to do it. Liverpool aren't the same
It's
team on the
a
counter-attack, and he's
fundamental
in a deep
aspect
position.
involving the
He's
use
ready to burst forward
of
at the
different sensors to
earliest
perceive
possible
the
chance when they
vehicle's
regain
environment.
the ball back.
While there are
We're getting plenty of the ball now.
While there are times, our project specifically focused on LiDAR. They emit laser beams to measure distance and create 3D maps on the surroundings. These sensors provide high-resolution point cloud data, enabling precise location and object detection. Perception plays a crucial role in ensuring both safety and efficiency on the road. Traditionally, it involved manual feature engineering and rule-based algorithms to analyze sensor data. However, modern ones rely heavily on computer vision techniques, particularly convolutional neural networks. Another key aspect is the use of depth information. Unlike traditional cameras, LiDAR sensors provide deep information, allowing perception systems to understand the spatial layouts of the environment. Let's now explore the bottlenecks architecture. First, unlike traditional approaches that may rely on pre-processed data, bottlenecks exclusively operates on raw 3D point cloud data. It works with voxels, which are 3D volumetric representation of the environment that provide a structured way to organize and process the data, facilitating efficient analysis and feature extraction. Then the technology also employs sparse feature processing techniques to predict those box features from voxelized input data. This allows for accurate location and classification of objects within the 3D environment. Bottlenecks also includes customized object class analysis capabilities to ensure adaptability to diverse scenarios and environments. The architecture incorporates detailed designs tailored for high performance in 3D object detection tasks, and the integration with CNNs enhances the architecture capability to learn complex patterns and features from raw sensor data. That will be all for my part, and then Vivek is going to talk about the last data sets.
I need to share my screen.
Okay, you can start. Just
is the presentation visible?
Yes, you can. You have to push the button for the slideshow, and you can start.
Okay. So, as Lucia has given a brief about voxelnext, and Luis talked about the NUSense dataset. So the next part would be: is the presentation visible?
Yes, you can.
So let's continue with the Kitty dataset. So let us begin with the brief description about the Kitty dataset and how the metrics were evaluated. So firstly, we were successful while training the Kitty dataset, and also we found some satisfactory results. And those results, we compared it with the different models from past 5 years. And we found that the results of our training was more or less satisfactory and was in the average range. So mostly we focused on only 3 classes, cars, pedestrians, and cyclists. So directly we can move on to the visualization. So the KITI dataset is mostly distributed in three different categories of difficulties. So we evaluated the model for each of them. The first image shown here is for the easy set. So as you can see here in the figure, we have in the left side we can see a sample image, and in the middle we have a bird's eye view, which is a top view of the prediction, and in the rightmost we have the prediction of the 3D bounding boxes. So for three classes, the green bounding box represents cars, the yellow cyclist, and the colored are for pedestrians. In the next, which is of a medium difficulty level, which includes a pedestrian. However, I think it is not clearly visible, but we have a car and a pedestrian, which was detected accurately. So raising the difficulty levels, we went more ahead. So as we can see, we have a lot of objects in the image, and the model more or less provided some accurate prediction of all the three classes. The next one, yes, we did it for the crowd, where a crowd of persons were present with cyclists and a lot of cars. And here we see that the predictions were equally good. So in the end, the conclusion, we found that the model could be much trained further. The model was trained for 40 epochs. It could be trained furthermore to provide more accuracy. And the next step of the project would be to go in a dynamic environment, that is, go for object tracking. That would be to provide the detections while the car is moving. So yes, that is all from our side.
Okay, thank you very much for your presentation. It's always a little bit hard if you're going on with online tools and different systems, but in a minute we will go on with a very nice presentation about development of a prototype for intraosseous infusion drilling machine. And it's a really nice project because the students had themselves the idea to do this project. So they heard a lesson here in the EU4M class about the application of robotics and medicine, and they saw this problem and went to their teacher and said to the teacher, it would be nice if we could implement such a thing. And that's what they actually did in their project, and we will see it in a moment.
Hi everyone, can someone confirm if you can hear me?
Yes, we can hear you.
Okay, so our project is called Development of a Prototype for an Intraosseous Infusion Drilling Machine. The intraosseous injection, also called IO, is a medical procedure where a fluid is injected into the patient's bone marrow, and it can be used in adults and children for several applications. But it is particularly useful in emergency situations, and the IO procedure basically involves inserting a specialized needle into the bone. This technique is employed when intravenous access is difficult or can't be quickly established, and as I mentioned before, particularly in trauma or critical care scenarios, where fluid or medication delivery is crucial for stabilizing the patient's condition and potentially saving lives. Next slide, please. There are several devices, but these three are the main ones using I/O. According to the state of the art, they were tested in a helicopter medical service to evaluate its success rate. We can see that the BIG is in the third place with a 55%, then the NIO with the 92%, and finally the ETSIO, which had the best performance with a 96%. But even though 96% is a good number, it surely needs to have something to improve, which is an extravasation problem. And this happens when there is a fluid leak from a blood vessel into the tissue. And it is pretty common in IO applications in case the drill doesn't penetrate enough to get to the bone marrow. Next slide, please. And that is why it is important to develop an assisted advanced drilling system detection where the classification of tissues such as vacuum, skin, bone, and bone marrow is possible based on signals captured during the procedure. Next slide.
Okay, can you hear me?
Yes.
Okay. Yeah. The core of the device is a ESP32 microcontroller. It will control the entire execution of the device. It controls the motors, read the sensors, and execute the control loop. The BMS, the battery management system, including the battery and the external power supply, are reused. It will be only necessary to add a step-down module to obtain the necessary 3.3 volt for the operation of the ESP32. Yeah. The actuation block here is made up of two motors, the linear advance motor and the drill motor. Both motors are connected controller using a driver. The power of both come from the 7.6 volts BMS module, and the voltage of the drill motors is 7.6 volts. This is provided by the battery. It's not a problem. The linear advance motor works with 6 volts, and the control loop will calculate the appropriate PWM taking account the upper limit of 80%. In the input and sensor block, we have a lot of sensor. The principal one, the Hall effect sensor, is using to count the number of the turns in the linear advance motor in the shaft. With the number of the turns, the linear distance in the drill can be calculated. In the input block, it is only necessary to configure in a special mode the end stop, because it's critical to know when the drill reach his physical advance limit. The last element here in the input block is the force sensor. This module measurement the force applied to the drill to regulate the forward speed in the closed loop. To convert this small variation into a useful value, we use a Wheatstone bridge. It's used to transform this small resistance variation of the sensor into a voltage variation. And this module here is a precision analog to digital converter (ADC) designed for wave scale, and the microcontroller obtain the measurement communication. To obtain the applied force, it is necessary to have previously execute a calibration algorithm. This is only needs to be done once during the programming of the device to know the conversion values of the force cells.
Yes, please switch on the camera.
Okay, can you
we want to
confirm
see
that
your
you hear me?
faces. Oh, sorry. Thank you for your presentation.
Yes.
Okay, So regarding the CAD system, we have to take in account several aspects. For instance, we start using a commercial drill, so we have to adapt an external case for a good interaction between this device and also the linear advance mechanism. We also have to make all the calculations for this linear advance mechanism. In this case, we use a lead screw connected to an M4 nut, which is connected to the mobile body, which encapsulates this commercial drilling system. Also, we had to take in account electronics that Solon slides. We had to make a good interface between the load cell, which measures all the resisting drilling forces of every tissue, and the rest of the components. We also design an own needle mechanism that is extractable from the main drilling system. And we also use, as Solon said, a limit switch to measure the 0-point reference, and also a Hall effect sensor to measure all the laps for the lead screw, which in the end measures also the depth of the drilling. So to take this in a, let's say, bigger picture, pass to the next slide, please. This would be the assembly of all the components. In this case would be the mobile body, which had the load cell and also the commercial drill. This would be the external structure and also the linear mechanism and the handle. And this is the final assembly of the whole component. Pass to the next slide, please. And finally, to see all the demonstration, we created a short animation of the whole operation demo. In the left image, you can see the forces of every tissue, the resistance to be drilled, and in the red line is the motor, or is the torque of the motor. So as we can see, to a continuous depth speed, we drill the 3 tissues, we left the needle fixed in the bone, and we extract the drill. And finally, we retrieve the mobile body to the 0 position. All this operation lasts around 10 seconds to do all the drilling part, which is a very short term, and also has this help to the user to avoid extravasation, which is the problem that Valerie was talking about. And pass to the next slide. And that would be it. Thank you so much for all the parents. Yeah. And see you soon.
Okay, so now next presentation about autonomous driving. I think we are already ready to go, so please go ahead. Yeah, we can already see you, so please share your screen and then start. Screen and then start.
Yeah, just 1 second. I'm having some trouble. Okay, there we go. Can someone confirm that you can see the presentation?
Screen and then start.
Yeah, just
Yes.
1 second. I'm having some trouble. Okay. Yeah, so welcome everyone. My name is Artur Abuda, And today, together with my colleague, Omer Abdella, with whom I have developed this work, are going to talk to you about our topic for the project Arbeit. And yeah, we have chosen object detection in adverse weather for autonomous driving. Autonomous driving has went a very far way since its origins, and now the technology is quite advanced, and the capabilities of autonomous driving are pretty advanced. But still, very big data sets and very big computing power is necessary. And we as students were looking for some area of research in this field that didn't involve so many resources. And therefore we chose kind of an application that was not so much explored, which is autonomous driving in adverse weather conditions. And yeah, through our limited resources, we could do some quite nice findings. So we basically took a state-of-the-art paper, we analyzed it, we dissected it, and as you can see here, the technique that we used for this project, or that was used in this paper, was datasets merging. So basically populate your dataset for training with just more data points, and that is expected to bring better results, which is not always the case, because sometimes it can lead to overfitting or high bias. But in this case, it actually proved that it delivered great results, and we wanted to check it. So we actually did all the process. We analyzed it. We studied it. And later, my colleague Omer is going to talk to you and walk you through some of the interesting results we got. But after doing this study, we went further into exploring this area, and we took a data set which is pretty popular called KITI from the KIT University, based also in Karlsruhe. And we basically first trained the model from the paper in this KITI dataset, and then we did another iteration in which we trained the model first on the adverse weather conditions dataset, and then we also trained it and tested it on KITI to see if results improved through transfer learning. In order to achieve this, we first had to do quite a lot of work in terms of data pre-processing and adaptation, and therefore we went into developing a custom code. And yeah, it is available on GitHub for everyone. We didn't see it actually done by anyone so far. So yeah, it was kind of an addition to our work. And I think thanks to this, we got actually quite interesting results. And now my colleague Omer is going to walk you through them. Thank you a lot for listening to me.
Okay. Hello, everyone. I'm going to take you quickly through the results. If you can confirm that you can hear me.
Yes.
Okay. So, as my colleague explained, we had I could say like three main objectives of this project. The first one is actually to verify the results that was obtained by the original paper, and to say, okay, this approach of data merging is actually working. And yeah, that was the first thing. As explained by Artur, we took the old paper, we analyzed the methodology they used, we had some comments on points they did, and then we reproduced their results actually. And yeah, it's quite typical to the original results they got in the first paper. And then we thought we could take this further, as it is like a new technology, not much have been done here. So we used what we call it transfer learning, or what the data scientists call it transfer learning. We first trained the model on the original, or we took a pre-trained model actually from the original baseline Cuckoo data set, and then we tested on the merit data set that we got from the paper and see the results. And then we tried to do a transfer learning using Kitty data set for one reason. Okay, we have a model and it worked fine in the adverse weather condition. We want to see if this actually could also improve the performance in the normal weather condition. And that's why we took this model, and we took YOLO V8, the nano version, and then we did the training on merit data set, and then we did it in Cuckoo, and we get actually good results, an improvement. It's a small improvement, but in the, let's say in the world of the machine learning, 0.01 is an improvement. So that's the first part. In the second part, we also try to explore with the new data set, or with the new model called YOLO V9, which is I would say, yeah, advanced and have more model parameters, but interestingly, it is not as fine as YOLO V8, and maybe that because of the number of hyperparameters this new model has, or maybe because of the nature of the data. So more tuning and further studies are needed to actually get a better result from YOLO V9. And to conclude this, actually, I would like to show a small video that demonstrate what we have done here. If I can open this, yeah. So this is the video of a car driving in an adverse condition, and as you can see, it is quite long, so I will make it short. Let's start from here. Even in this adverse, or let's say stormy weather condition, you can still see that the car is actually being detected. And yeah, that concludes the work for our project. So thank you.
Thank you very much. Thank you for your presentation. Thank all the students for the presentation and the work they put in their projects, and also in the presentations. I just had a look on the chat, and yeah, there are quite a few. I see also there are people from former editions, so it's nice that you're still connected to us. But at the moment, I don't see any questions in the chat. So my question would be, are there any questions here in the room about the presentations? Any special issues? Yes, great. Somebody's brave.
I have a question to Eduardo and the high efficiency project. And did you learn FEM with a course, or did you do it within the project? Because it's pretty impressive.
Thank you for your question. Well, in my case, I work with FEA since bachelor's. Also, when I was working, I also did some projects related to that topic. So that's where I learned pretty much. It was really free, this project, in terms that we knew our goals and what we needed to do. And I think everyone from the team members, they put what they knew to contribute to the project, but we didn't receive like any capacitation or any course regarding that. So yeah, I would say it's previous experience.
Thank you. I also have a question to this team, because they entered here as EU4M student into the German team. So what's your experience with facing students that have been here for the whole bachelor studies and you entering? Was it a nice experience, or what was your experience?
Well, for my part, it was very interesting to see like the knowledge that I brought to compare it to in our case to a German student, like because he, at least in this case, he has a very similar knowledge, but with a different point of view, and I think that's very good to experience.
Yeah, same. Like it was pretty interesting. Well, in my case, it was my first time working in a project with people from Germany. I worked before with people from the US, but yeah, of course, it's the same side of the world. But yeah, from people from Germany, yeah, it was pretty different. But I would say it's, as Ignacio said, it was quite interesting because many of the times we reached to the same conclusions, but doing different procedures. For example, in our case, our colleague Peter, he was more a person of physical things, like tangible things. So he built like physical models, like he called it cardboard engineering. He did like models done by with cardboard. And me and Ignacio, for example, we were more used to working the CAD beforehand. So those kind of things. But at the end, we reached the same conclusions.
Great, thank you. That's always interesting to see what are these intercultural experiences. So anyone else who has some questions or wants to share his experience with us working in projects? So for example, with OptiSkate, how did you come up with this idea?
So for OptiSkate, it is actually our group leader, Ignacio, is a professional rider, and he likes to skate, but he didn't find a better solution to teach someone with a more easier and effective way. So we find an example to integrate the mechatronic system, a real mechatronic, with the hardware, software, and electronic parts, as well as the software. So even though this is a small project, but it integrates all the knowledge that we need for the mechatronic system. Yeah, it's interesting also when we're testing and we did the simulation, we have the chance to skate for a little bit well, and found out that it's not really easy to learn how to skate. Yeah, it is a fun group project.
Okay, thank you. And talking about VR, how did you experience this thing when you come to Karlsruhe? I don't know if it's taught in so many universities. You liked it?
Hi, yeah, well, actually my experience was that my team came from Mexico and one student was from South Korea. We had no previous experience, but we came to the realization that it was pretty easy to learn when we had the chance to really apply it into a program. We went with no knowledge of it, and we figured out that there's a lot being done in VR in the world, so we were pretty excited to find the resources and then to apply it to a project and see the results.
Great. Thank you also for sharing your experience. And anybody else would like to give comments, ask questions? Yeah, sure. That's our guest lecturer from Malaysia, actually.
Okay, this is actually questions for the how to spell out, how to pronounce it. Maroon Waldes. Maroon Waldes. All right, I have questions on how you measure the 50% reductions of energy.
The main part of my project was the theoretical part, and because I didn't have much time to talk about it, I couldn't talk about how I calculated. But the main thing is, I calculated the energy from the wind and from the solar cells, and then compared it to the behavior of the wind speed sensor, because it has, for example, it sends the information every 3 seconds and had a standby time, and so I analyzed how much energy it used, and then how much energy I could earn. And then I also knew about the capacity, the old capacity of the battery, and then I could come to the conclusion of 50%. But in the calculation, it was also it was pretty difficult because there were many parameters to look at. For example, the different operating height and the wind speed data on different times of the years, and also stuff like the iteration, the angle in which the iteration can. There were many parameters, and then I needed to short it down to how much energy I won and how much energy it took for the wind speed sensor, and then I could come to a conclusion. It's difficult for me in English, but yeah. No, definitely not. It's based on the data I used. So I used, for example, I used the same data for the iteration and then for the wind speed, data from the same year. So it's a little more comparative. Yes, you could compare it a little bit easier, but it also could change pretty easily in the next year and the next year. But I did the base calculation to someone else in the future could use my calculation to calculate it for the other years with the other data. Yes.
Okay, thank you. Any more questions? Okay, then thank you again for sharing your project, sharing your experiences with us. And I hope you go on working so dedicated, and yeah, all the best for the rest of your studies. Thank you for watching us. I hope that you enjoyed the presentations, and goodbye.